Good morning, everyone. Some of you might recognize me. I was one of the founders of the RISC-V Foundation 5 years ago, together with the rest of the great folks behind this technology. And it's a pleasure to be here to talk to you about another organization that we started in the spring called the Open Hardware Group. But before I start that, every time I've given a talk at a RISC-V event, I'd like to get an understanding of how many people are in the room for the very first time first time that they're at a RISC-V event. Well, that's kind of interesting. Okay. How many people in the room have a project right now using a RISC-V device? Oh, an equal number. Very cool. So one of the challenges, or probably not necessarily a challenge, the most frequent questions I got when I was running the RISC-V Foundation was, hey, you, RISC-V guy, where's my core? Give me the core. Because a lot of people, when they originally got exposed to the RISC-V ecosystem, thought that the RISC-V Foundation was implementing devices, right? But the RISC-V Foundation is specifically focused on developing the set of specs. Basically, the product is a bunch of PDFs, right? Which is good. So it's a spec-focused organization, and then we love many, many implementations, and love all implementations, open source, closed source, proprietary, for-profit, non-profit, doesn't matter. The more the merrier. That's the premise behind the foundation. So we'll talk about that. I want to walk you through the challenges of adopting open source IP. Certainly in the software industry, this has been figured out a long time ago. In the hardware industry, not for the lack of trying, you cannot point to any high volume SoC today that uses a piece of open source IP that was downloaded, off a GitHub repo or whatever. There is no open source IP in high volume SoCs today. And let's talk about why. We'll talk about the Open Hardware Group organization and a family of open source cores called Core 5, and an announcement we made yesterday to help try to address some of these challenges. And then I'll show you some of the members who are on the show floor. So this is a chart that I took out of an ARM blog post that talks about the costs associated with developing SoCs. And if you're in the high volume SoC business in deep submicron technologies, you're very familiar with these costs. Over 90% of the cost is around the actual development, verification, and physical design of the particular IP blocks that you're using. And for high value differentiating IP blocks, that's warranted. But for some of the stuff that is sort of table stakes, generic embedded controllers, those kinds of things, maybe we can share a little more easily in the ecosystem and use those open source artifacts. So what are some of the barriers? Well, the quality of the IP. If you work in a chip design team, you're not going to take your corporate badge, walk into your boss's office, plop it on his desk and say, hey, I bet my badge on this nice core I just downloaded from a really cool university GitHub repo. Let's put it into our SoC. Let's go to production. This will be wonderful. Beyond that, what kind of roadmap are you going to get for that IP? What's the ecosystem going to look like? Are all the development tools available? Do you really have everything that you need to support that device in high volume applications? And then maybe just as importantly, but on the business and legal side, every major silicon company has a treasure trove of IP and patents in a portfolio. If we don't have permissive licensing, and this kind of offends some of the true open source folks, but if we don't have permissive open source licensing where they don't have to give back from a legislated standpoint, where they give back because they're incented to do so, because they see benefit, then they won't join. So on top of that, there's really not been any opportunity to build open implementations because some of the very fundamental underlying pieces of IP, like an ISA, have not been open. So the RISC-V ISA comes along, and it really brings in a new frontier of open innovation because now there's an open ISA, no problem, right? So Zvonimir and I could start a processor company in Zvonimir's kitchen tomorrow, and we could download the RISC-V ISA spec, pop up a core on GitHub, call it open source, and Bob's your uncle. That's great. That's great open innovation, many more cores. I think Helena showed that there's now 69 cores on the RISC-V website right now, many of which are open source. How many do we really need? If you look at, cast your mind back 20 years or so at the beginning of Linux, there were many distributions that were starting to emerge as Linux sort of came onto the scene. And today there's 5, 6 that people really care about. That's going to happen in this community. So these tables are a couple of months old, there's more, but these are all of the open source cores that are popping up in the RISC-V ecosystem. And like I said earlier, that's good for innovation. The barrier to entry is very good. The challenge is, from an ecosystem standpoint, they won't all survive. The ecosystem cannot support all of these cores. So there's certainly an opportunity here to organize ourselves around cores that make sense to our companies, to our business overall, and collaborate on that. And that's what Open Hardware Group is about. In particular, the RISC-V core and Ariane cores, those are the names of 2 very good quality cores written in System Verilog, developed by the great Pulp platform team who has presented many, many times at RISC-V events at ETH Zurich under the lead of Professor Luca Benini. So that's a little bit of what we're doing and why. Open Hardware Group is a nonprofit organization, a separate nonprofit organization and legal entity that has the right to govern its own direction. It's not a project of another organization. With the focus on specifically making high volume production SoC ready cores that actually stitch into commercial CAD tool flows. More than 95% of today's volume in the semiconductor industry is developed in a traditional, whether it's good or bad, we can have that discussion later, but that volume is developed in a traditional System Verilog-based tool flow, supported by one of the big 3, or usually a mix of the big 3 CAD guys. So if we want to increase the adoption of open source IP, go back to my comment at the beginning, there are 0 IP blocks used in high volume SoCs today. Open source IP blocks, sorry. If we want to go really take a stab at addressing that, the focus of our organization is to just provide an IP block that is well verified and fits easily into existing commercial CAD tool flow so they can be adopted by high volume SoC guys. So we got lots of companies involved. We tried to, at the beginning of forming the organization, which we announced in June at the Zurich workshop, by the way, over the course of the summer, we worked with these companies to define the bylaws and governance framework for the organization. And we have a cross-section of companies covering systems guys, semiconductor high volume SoC guys, tool chain guys, to make sure that we had a good representation, that the organization would be structured such that all of these companies' needs would be met as we deliver these open source artifacts. Many of these companies are here in the Open Hardware booth on the exhibit floor, and I'll walk through some of the demos that they'll have in their, at their stands towards the end of the slides. We also have a pretty healthy group of partners helping us manage this. So on the infrastructure side in particular, I want to point out the Eclipse Foundation. So many of you are probably familiar with Eclipse from an IDE standpoint. The foundation manages all kinds of projects. We're partnered with them, not a project within the Eclipse Foundation, but we're partnered to reuse some of their engineering release process, which is well proven. And the Verilog, System Verilog simulation environments that we're hosting to verify the cores are run on IBM Cloud. So the cores in particular, and I think for those of you who held your hands up already, that you had been to multiple RISC-V events and you're familiar with the ecosystem, the Pulp platform team out of ETH Zurich has done a very, very credible job with their 32-bit and 64-bit implementations. These cores, if you will, are graduating from university. They're growing up, if you will, and leaving school. The Open Hardware Group is taking over these repos and managing the verification work together with our member companies to produce what you'd expect to see in high-quality commercial IP that you'd be licensing. And just to give you a flavor, all of these cores, both of these cores, I should say, have seen silicon before. Every one of these tape outs has used the 32-bit core. All of the named tape outs were done by the team at ETH Zurich. GreenWaves has a production product around the 32-bit implementation. NXP's had a Vega board out for a while that uses a 32-bit implementation. Half of these tape outs have also used the 64-bit Ariane core. So these aren't nascent, first use cores by any stretch of the imagination, but nor are they verified to the extent that you would expect out of commercial IP, and that's what we're working on. We have a board of directors that is pretty active in helping guide and direct the organization, a very transparent organization. And we're pleased to have systems guys, chip guys, tool guys at the board as well. And like most organizations, we're organized around working groups. We have some technical working groups and marketing working groups, and in particular, a cores task group that decides on the functionality going into the cores, the verification task group that lays out how we're doing the verification work and sharing it amongst the members, and then a platform task group for bring up environments and so on as we bring the cores to life in real chips. So one of the focuses for the organization is from synthesis to silicon. So we're going to leverage commercial tool flows and produce real devices for evaluation to let people experiment with the cores in real silicon. And that brings me to the announcement that we made yesterday together with NXP. We announced a project for the 2020 calendar year. And if you're not familiar with the term BHAG, we set a BHAG for our organization. It's a big, hairy, audacious goal. And it's meant to scare you at first, make you shake your head and go, what the heck, are you kidding? You're crazy. And then after you get over the you're crazy part, you kind of hopefully cast your mind to, well, how are we going to do this? If this is really something that we're going to try to achieve in the calendar 2020, what are the things that we need to do? So we're in the process of organizing the resources within the Open Hardware Group around having a production-ready SoC that includes the Core 5 CV64A, which is the Ariane core, and the CV32E, which is the RISC-V core, in a deep submicron SoC on an eval board, running relevant software that we'll have taped out by the end of next year. By the second half of next year. And it's obviously a pretty nebulous time frame. We have some more definition work to do before we can lock that down, but we wanted to announce the project so that we can encourage participation as an open industry call to participate in this. So this is what the device looks like. The good folks at NXP have basically donated a production class IMX processor to us. We're not open sourcing all of the peripherals. We're not trying to solve world hunger with open sourcing SoCs. We're not working on any open source tools either, as an example. The gray stuff in the middle around the cores is what are the open source artifacts. But we need to have a real SoC relevant system that we can bring these cores up in and get the community to be developing software around this. So we're very, very pleased with the collaboration from NXP around this, and many more details to follow. If you're interested in this project, please come see me over the course of the day. The ecosystem that we've got wrapped around this thing is pretty good, pretty impressive. Like I said, we tried to initially recruit companies across the breadth of the ecosystem from a system standpoint and from a silicon standpoint, from a tools and software standpoint. So it's a busy chart, but the result at the end will be there's that little block diagram of the Core 5 chassis on a board running some relevant software. So we're pretty excited about this. It's certainly not something that the semiconductor industry has done in a collaborative fashion before. So it's not going to be for the faint of heart. That's why it's called a BHAG. So with that, here's a few areas of participation that we would welcome more contributions around. Certainly the verification aspect is the long pole in the tent, and we've got a lot of work to do around the Ariane core from a bus interface and coherency standpoint. We're also looking to maybe make some instruction for clock improvements around on the 64-bit core, and there's obviously always software and OS work to be done. So come join us and play in the sandbox, so to speak. So I'll quickly flip through who's here in the booth. So come visit us. So the BlueSpec guys are showing off their RISC-V factory, which is a very impressive way to evaluate multiple different cores, including the RISC-V core. The team from CMC, which does a lot of support work for universities and CAD tools, is here, and they're using the Core 5 cores and distributing those into universities. The Embecosm team's here with demoing MBench, right? A new benchmarking standard that Jeremy has been working on with Dave Patterson from a development standpoint. So that's being demoed on the Core 5 cores, the RISC-V core in particular. The GreenWave guys have production devices that are based on these cores and are here showing the GAP8 processor. The Metrics guys, you probably recognize this chart, right? So Metrics and Imperis are very active. In fact, we started working together on this quite a while ago. We're also going to leverage the good work that the Google team has done, and this is running in IBM Cloud. So come and see this verification test bench. It's actually pretty interesting. And then NXP is talking about a lot of the innovation work and adoption work that they've been doing to try to drive open source adoption of RISC-V. Last but not least, the Huntsman team has done really, really excellent work, a formal verification work around these open source cores. In fact, they found in the order of 13 different issues when doing some formal work, which are being worked on. So they're a great contributor to this effort as well. Come and see them. And this is pretty much the end of my talk. Summary slide around what the organization is about. A lot of activity underway. As I said earlier, over the course of the summer, since we announced the organization in June, we were working on closing off the membership agreements and bylaws and getting that defined and ratified by the board of directors. That work is all done. If you're interested in participating in this work, we'd happily have you join the organization. So go to the site and you can get information on membership, or you can see me here over the course of the day and be happy to answer any questions you might have. That's the end of my talk, and I think I've got a few minutes for questions if anybody wants to step up to the mics.
I see for the open hardware is going to have a bunch of costs. So like this kind of a non-profit group, I think the major part is how do you ensure the quality. So you mentioned the verification plan. Would you please explain more on the verification plan? If we can share the verification environment and test case is very convenient for the core developers, I think.
Right, so if I think I understand your question, you want to know how we're going to share verification work and show the quality of the course?
Yes.
Yeah, so the verification work that we're doing is on commercial grade CAD tools, but all of the stimulus, all of the verification infrastructure around that and scripts, that's all open sourced. So we'll have our own instance of a System Verilog simulator running in the cloud where we run this test bench, and you'll be able to take all of the stimulus around that test bench and install it on your premise and with whatever System Verilog simulator that you use to recreate that if you want, or just participate in the work that we're doing, push your test cases up into the cloud within the Open Hardware Group, and we'll run them there. And all of the coverage, functional coverage and toggle coverage and everything of and effectiveness of those tests will be shared openly.
Okay, thank you.
Okay.